Hello, everybody. This is Sunday. It's May 29th, and we are heading into week 4 of our online astronomy course. I'm sorry I couldn't post a live video last week. I had a medical emergency, but as you can see, I'm recovered, so life is good, and I'm happy to be with you this week. I did post, though, an older video about the Module 3 material. I posted that late last week. And so if you haven't, please take a look at that too, because it does deal with Newton's laws, and I think it'd be worth looking at. So what's ahead in Module 4? Well, in Module 3, you learned about Newton's laws of motion. You learned about his law of gravity and how astronomers use those laws to find out how objects move, how planets orbit stars, how stars orbit each other, how stars orbit the center of our galaxy, all sorts of things. So Newton's laws are what we use to understand how the universe works. But what information can we get from the light itself? What is light? And you're all used to light. That's all you have ever seen in your life. But what do we mean when we say light? Now, sometimes I'll use the word radiation. And to an astronomer, light and radiation mean the same thing. So if you hear me say radiation, I just mean light. But what is light? What is light made of? Is light made of something? And the answer is yes. Light is made of electrical and magnetic energy. And you're used to electric and magnetic fields. Magnetic fields, if you've ever used a magnet just to pick up a little paper clip, or electric fields, if you've ever taken, a load of wash out of the dryer and the hairs on your hands stand up, you're feeling the electric field around those socks. That's just due to electric charges on those socks. So there's magnetic fields, there's electric field, and light consists of electric and magnetic energy due to those fields. And so light consists of that energy, and that energy travels from a source of light to your eyes. Now it happens that that light isn't in a steady stream. Those magnetic energy and that electrical energy pulsate as those light rays move towards you. And they pulsate very fast. There's about 100 million vibrations of the light. And by vibrations of the light, I simply mean the pulsing of that magnetic and electric energy. But 100 million of those pulses per second. So really fast. Now, sometimes you'll see light depicted as a wave, and people talk about light waves, and that's right. And so in your book, you might be shown something like a light wave that starts here and then is shown to travel in a wave-like pattern. That doesn't mean the light ray itself is actually traveling in a wavy pattern. What those waves show you is how the light is pulsing. So if you're looking at the light starts over here, and it shows the wave getting large, that means there's a lot of magnetic and electric energy at that point. And then when it goes down and then back up, anytime the level of that wave moves away from just a straight line, that means that there's a lot of electric and magnetic energy there. So that's how to think of light. That's one way of thinking of light, as this pulsing electric and magnetic energy that's traveling out towards you. Now you might ask, well, okay, yeah, that's what it is. Light is made of energy, but still, what carries that energy? What carries that energy? And it turns out that light is made of massless particles called photons. That's all a photon is. It's a massless particle of pure energy. But nevertheless, each individual photon has a frequency that tells you how many times per second it's the amount of energy is changing. So every photon carries energy, and it has a frequency that tells you how rapidly that energy is changing. So how about our light wave? That light wave that starts over here and travels across. Okay. Where there's along that straight line, that shows which way the wave is traveling, along that straight line, that's where really there's very few photons. But where you get a lot of photons is where the humps are high or low. And at those points where you have a great departure from that straight line, at the top of the peaks and at the bottom of the valleys, that's where you have a lot of photons. So, why doesn't the world look grainy? Well, gosh, just from a light bulb, there are hundreds of billions of photons that strike your eye every second. And so the world looks smooth to us. It doesn't look grainy. Although if I could take a picture with a really fast camera and just capture like 10 or 100 photons, it really would look grainy. And that blinking, those 100 million oscillations per second are just too fast for our eye to see. Now, there's all sorts of light. And you can talk about the frequency of the light. That's one way of talking about the light, the number of oscillations per second. You can also talk about the wavelength of the light, and that is the distance from one of these peaks to the next peak, the physical distance. And so what is the wavelength of light? Well, it depends upon what sort of light you're talking about, because there's a large, wide spectrum of light. Now, spectrum simply means the total types of light that there are. And the spectrum of light, what sort of light you have depends upon the wavelength of the light. And you can see the spectrum of sunlight here right behind me. And so right behind me here is the spectrum of sunlight, a rainbow. And this just shows you all of the colors of light that are coming from our sun. There's at the lower end where my thumb is, it goes from a violet, and at the other side of the rainbow, it's red. So all those colors and all the ones in between belong to the spectrum of visible light. And what defines exactly what color we're looking at is the wavelength. So the red wavelength that you see up here at the top of the rainbow, right around here, there we go. Yep, right around there, the wavelength is about 700 billionths of a meter. Now, we don't want to say billionths of a meter all the time, so we have a unit for that, and it's called a nanometer. A nanometer is a billionth of a meter, and so the wavelength of red light is about 700 nanometers. And the wavelength of blue light down here and violet light is about 400 nanometers. And you might be wondering, well, gosh, yes, that's visible light. Are there other colors of light that we can't see? And yes, there are. If I look at the red side again, if I go beyond the red side, I go into longer wavelengths, longer than 700 nanometers. I get into infrared light. And even further, even longer wavelengths, I get into ultimately microwaves, radio waves. Now down on the blue side, if I move to smaller wavelengths, then the violet, the purple light, that's about 400 nanometers. If I go to even shorter wavelengths, then I get into ultraviolet wavelengths. And from there, I get into X-rays and gamma rays. And you know, these terms rays, why do we call them rays? It's historic. Astronomy has a lot of historic baggage that comes with it. It's one of the oldest sciences. And so we call those parts of the spectrum X-rays and gamma rays. It's completely historical. All light is the same. All light is made of vibrating electric and magnetic energy. Well, that is pretty cool. But what is even cooler is all the information that light carries. So what I want to show you here, I'm going to share the screen, and I want to show you what happens if you really took a look at sunlight and really stretched it out. So we're going to do that. So I'm just going to share the screen here. And take a look here. Here is, at the bottom is the blue part of the spectrum. So this is the short wavelength end of the spectrum. And it just moves along, the wavelength getting longer, going through the green, through the yellow, through the oranges and the red, till we end up with the long wavelength end up here at the top. And you might notice that there's all these dark lines in the sun's spectrum. And you can see all these, astronomers study these lines just by passing the sun's light through a prism, which is just a triangular piece of light that spreads the different colors apart. Or they use something called a diffraction grating, and that's another device that when the light passes through it, it gets spread into its different colors. But they can really look at the details of all these dark absorption lines. So why are those lines there? And to explain this, I have to go back and talk about the source of light a little bit. Now, in astronomy, there is one source of light that is most important, and that's the one we're going to be talking about. It turns out that any object that has a temperature above absolute zero, and that's everything, gives off a continuous spectrum. That means light of all colors. And that radiation is called blackbody radiation, sometimes called thermal radiation. And you're giving that off right now. I mean, you have a temperature above, I hope, absolute zero, and you can feel it. So just take your hand out in front of your face, palm facing your forehead. Oh, go ahead. And slowly bring your hand toward your forehead so you're not quite touching. Do you feel that warmth? That is the infrared light that your body is giving off. And in fact, right now, you are shining with as much energy as a 100-watt light bulb is. It's not visible light, it's infrared light. That's part of the light that we can't see. But still, you are shining. Now, if you have an electric stove where you turn on a burner, and as you turn it up, you might notice that at the beginning, it just glows a dull red. But as you increase the temperature, it glows hotter and hotter. And your stove won't get there, but if you heat up a piece of iron or anything really, if you heat it up, it'll glow white hot. And it turns out that the color of the light that a hot object gives off, the color depends upon the temperature. And as it happens, hot objects give off a lot more blue light, whereas relative cool objects give off more red light. And that's what causes stars to have different colors. Hot stars give off more blue light, so they look bluish, and cool stars give off more red light, and so they look reddish. So this is blackbody radiation. What you see in this rainbow that's right here behind me is the spectrum of blackbody radiation for the sun's light. The sun's giving off continuous blackbody radiation. That's what sunlight is. But again, going back to this close-up of the sun spectrum, let's take a look. Here it is. You see all these dark lines. And this is one of the greatest tools astronomers have to study stars and to study the universe. And here's the idea. You know, our sun is very hot. It's about 5,770 degrees. These are degrees Kelvin, meaning degrees above absolute zero. But that's very hot. And the sun is giving off visible blackbody radiation. But above the sun is a cooler atmosphere. And as the sun's light passes through that cooler atmosphere, atoms in the atmosphere can absorb light of just certain wavelengths. And that removes light from the spectrum. And so you see it here as these dark lines. What's actually going on in the atoms that are in the sun's atmosphere is that a photon of light comes in, hits the atom absorbs that energy by having an electron jump up from a lower to a higher orbit in the atom. And that removes the light and helps produce that dark line. And it turns out that every element produces different dark lines. It's like every element has a fingerprint, a spectral fingerprint of these dark absorption lines. And so by looking at the spectrum of the sun, we can tell what the sun is made of. We can tell what other stars are made of. Not only that, we can tell how much of each element there is. And all of this about how atoms can absorb and emit light and how objects give off blackbody radiation. I've made 3 videos for this module about that. And I demonstrate that with a light bulb that I can turn up. And you can see how the spectrum of the light bulb changes as I increase the temperature of the light bulb's filament. So please take a look at those videos. And you know, there's even more information in that light. As a star moves toward or away from us, and a source of any light moves toward or away from us, what happens is that as the star is moving towards you, it's catching up with its own light waves. It's compressing the wavelengths, making them shorter, and making the light look bluer. And those dark absorption lines that you saw in the sun spectrum shift toward the blue end of the spectrum. Now, on the other hand, if the source of light is moving away from you, it's moving away from its own light waves, and that stretches them out and makes them longer. And so the light looks redder, and those absorption lines are shifted toward the red end of the spectrum. Now, the stars in our galaxy are moving much too slowly for this to have a big effect on their colors. So the colors of the stars that you see in the sky And all of those stars are in our own Milky Way galaxy. All those colors are due to the temperatures of the stars. But when we come to make observations of other galaxies later in the course, this Doppler shift, as it's called, is going to be very important. And, you know, this was first noticed by a man named Christian Doppler. And he noticed that when a source of sound, he actually put, this is amazing. He had a railroad car, and he had somebody playing a trumpet on a railroad car, and that railroad car went past him. And trumpet was blowing a note, and he noticed that as that trumpet was approaching him, the pitch was higher. And as it moved away, the pitch was lower. Maybe you've noticed the same thing if you've ever seen at a train crossing and the train passes by and blows its horn. When it's approaching you, it has a higher pitch, and when it moves away, it has a lower pitch. Sort of like meow. I love doing that. I got to do it again. That's the approaching part. Meow. That's the moving away part. Higher pitch approaching, lower pitch moving away. For light, bluer light coming towards you, redder light moving away. So I hope you learned all about this. I hope you enjoy learning about it. All astronomers can do is look at light. So we have to understand it as well as we possibly can. Now, before I go, I do want to take a quick look at stellarium. So let me pull up stellarium here. And just a second, I will share the screen. And there's stellarium. Okay, I've set it for midnight. And this is midnight on, for the end of the week. What day it is? This is midnight on May 2nd. But we're looking south. And I just wanted to show you two stars you could go out and look at. This is looking south. And there are two stars in the sky that are prominent. There is Antares here in the constellation of Scorpius. And there is Spica, which is in the constellation of Libra. Here, I'll show you the constellations here. Put them up real fast. I'm sorry, Spica is in Virgo. Excuse me. But here they are. Here is Antares in Scorpius and Spica, which is in Virgo. And here's here again are the figures that go with that. But I want you to go out if you have a chance, and the sky's clear. That's why I've chosen later in the week. And you know, you can go out earlier. I just don't know how close you are to the mountains. So this is late enough that stars should be clear of the mountains, certainly if you live close to mountains. That Antares here is a very red star. It's a red giant. Whereas Spica is a very large blue star. And so Antares, a red giant, is, because it's red, you know, its surface is very cool, relatively cool. And Spica, because it is looking blue, is in fact very hot. And so go out, take a look through binoculars, because you can see the colors a little bit better through binoculars. Take a look. Anyway, as always, if you have any questions, you know how to contact me. Just send me an email, and I'll be happy to set up a Zoom meeting. You can come to my office and have a meeting in person if you'd like. So I hope you enjoy learning about light, and I'll see you next week. So everybody, take care, and I will see you next time. So until then, bye-bye.